welcome to this video of AQA P1 revision covering waves in our universe and some how science works factors. So we'll start with the general properties of waves. We've got two types of waves here, but both types transfer energy, and that's the general property of waves. Waves are something that transfer energy through vibrations or oscillations. So the first type of wave we've got here is a transverse wave, and that's the wave that you see going up and down. Key features that you need to be able to label on this wave: we've got peaks, also known as crests, troughs at the bottom. The height of the peak from the centre line or equilibrium position is called the amplitude, and basically that tells you how much energy the wave has. And then the distance from one peak to the next or one trough to the next is called the wavelength, literally the length of a wave. So the definition of a transverse wave, which you'll need if you're higher tier, is it's a wave in which the direction of oscillation is perpendicular to the direction of energy transfer. So in this diagram, the energy transfer would be going right to left, say, but each of the particles that are vibrating up and down. So it's at right angles to the way the energy is going. An example of this type of wave would be any part of the electromagnetic spectrum, so radio, microwaves, ultraviolet, infrared, visible light, X-rays, gamma rays. So, for example, electromagnetic waves. Then our second type of wave is the longitudinal wave. And that's the type of wave that is made up of compressions, where the particles are close together, they've been compressed together. And where they're further apart is rarefactions, which I remember as the particles are rare, there aren't very many particles in that space. So they're rarefactions. The wavelength in a longitudinal wave is the distance from one compression to the next compression, or from one rarefaction to the next rarefaction. The definition of a longitudinal wave is a wave in which the direction of oscillation is parallel to the direction of energy transfer. So we can see there they've annotated that the wave direction is left to right, and the particles are vibrating backwards and forth in a left to right manner, so parallel to the direction that the energy is being transferred in. An example of a longitudinal wave would be a sound wave. The other key feature of waves that you need to know about is their frequency. The frequency of a wave is defined as the number of waves passing a point, or the number of oscillations per second. And the unit of frequency is hertz, which is capital H, little z. Remember to give it a capital because it's a guy's name. So what things can we do with waves? All waves can be reflected, refracted and diffracted. Here we are starting by looking at reflection. And so in our first diagram, we've got a mirror and the ray coming in hitting the normal. Okay, so the normal is a line perpendicular to the surface of the mirror. So where the ray hits the surface of the mirror, we draw at right angles to that point on the mirror a normal, and we measure our angles to the normal rather than to the surface of the mirror. So the ray of light coming in is called the incident ray. The ray of light coming out is called the reflected ray. And the angles between each of those rays and the normal are the angle of incidence and the angle of reflection. And the law of reflection tells us that those two angles have to be equal. In this second diagram, we're showing how the rays can be used to find out where the image is. So we draw two rays coming off of the object at different angles. Each of those hits the mirror and we draw a normal. They follow the law of reflection, and we trace those lines back to show where the virtual image is formed. Okay, really important when you're doing your P1 exam that you have your protractor with you so you can measure those angles, and you've got a ruler for drawing those straight lines. A pencil is also useful. Okay, so refraction and diffraction. Refraction is our first diagram on here, and diffraction is our second diagram. So we'll start by talking about refraction. Refraction is when light bends because it's travelling from one material into another. So for example, It might be from air into glass, it might be from water into air, any place where it's changing direction because it's changed what material it is. And that's because the speed of the wave changes in those different materials. So the angle between the incident ray and the normal is known as the angle of incidence. The angle between the refracted ray and the normal is known as the angle of refraction. If we're going from a less dense substance into a more dense substance, for example, air into glass, then the angle of incidence is going to be greater than the angle of refraction. We say it's bent towards the normal. If we are moving from a more dense medium into a less dense medium, for example, water into air, then the angle of refraction is going to be bigger than the angle of incidence. We say it's bent away from the normal. Okay, diffraction is when you have a wave passing through a gap. So the size of the gap matters, as you can see in this diagram. But what happens as the wave passes through the gap, it spreads out. Okay, that would be the definition. And for the optimum amount of diffraction, we want the size of the gap to be similar to the wavelength of the wave. That's what's going to cause the greatest bending. So you can see there on the right hand part of the diagram, the narrow gap, which is closer to the wavelength of that wave, is producing much greater diffraction. The wave is spreading out more. Okay, really important when you're drawing these diagrams to make sure that you show that the wavelength, the distance between those wavefronts, is the same each time. Moving on to sound waves. Okay, so sound waves can all do the same things as light waves. They can reflect, they can refract, and they can diffract. But sound waves are a longitudinal wave. Even though sound waves are longitudinal, we often represent them as a transverse wave to make life easier for us. Sound wave is caused by a vibration. Okay, so vibrations of particles. So sound can't travel in a vacuum because there are no particles there. If a sound wave is reflected, we call that an echo. Now the device that we use in order to see the properties as a transverse wave is called an oscilloscope, and you might be shown oscilloscope traces like the ones below and asked to interpret them in order to describe the sound that's produced. So the frequency of the wave, the number of waves per second, tells us the pitch, and the amplitude or height of the wave tells us the volume of the sound. So if we look at these waves, we can see that wave 4 is going to be the loudest because it's got the highest amplitude, whilst wave 5 is going to be the quietest because it's got the lowest amplitude. Then in terms of pitch, the highest pitch is, the lowest pitch first of all is going to be wave 1 because we see the least waves in that space, and the highest pitch is going to be wave 5 because we see the waves pushed together the most. There's the most number of waves per second. This leads on nicely to the electromagnetic spectrum. As you might know from the song that we insist on playing to you over and over again, it's just the name of a range of radiations: radio waves, microwaves, infrared radiation, visible light, ultraviolet, X-rays and gamma rays. If you are doing higher tier, you will need to know what the range of what the range of wavelengths is. And for any tier, you need to know that all of them travel at the speed of light. Often they'll try to catch you out and they'll talk about a question, which one has the higher wavelength, which one has the highest frequency, which one travels fastest. They all travel at the same speed. But you can see from the diagram that gamma rays have the shortest wavelength and the highest frequency, whilst radio waves have the longest wavelength and the lowest frequency. Okay, frequency is associated with energy, so higher frequency also means higher energy, so that comes from the gamma rays. So the wavelength of a gamma ray is 10 to the minus 15 meters, and of the longest radio waves is 10 to the 4 meters. If you're doing higher tier, that's what you need to learn. You don't need to know the wavelengths of each individual part. Okay, what you might need to know is how to convert between the different prefixes like kilo, etc. To convert your numbers into meters or into hertz for doing calculations using the wave equation. So 10 to the 3 meters is kilometers, 10 to the minus 3 meters is millimeters, 10 to the minus 6 meters is micrometers, that's a Greek symbol mu, 10 to the minus 9 meters is nanometers. And then in terms of frequency, the ones that you'll probably see come up are kilohertz is times 10 to the 3 hertz, megahertz is times 10 to the 6 hertz, and gigahertz is times 10 to the 9 hertz. You'll notice there that all of these have multiples of 3 as the power. The only time you won't have a multiple of 3 is when you're looking at centimeters, which is 10 to the power 2. Okay, so radio waves, uses of those for communications are for TV and radio. Microwaves, you need to know the uses of mobile phones and satellite communications, satellite TV. Okay, that's because the microwaves can pass through the ionosphere, which radio waves can't. Infrared, the use that you need to know is in remote controls. And for visible light, the use you need to know is photography. So there might be questions asking you for uses, and those are the ones that will be on the mark scheme. Those are what's in the specification. You won't be asked for uses of gamma rays, X-rays and ultraviolet. Okay, so redshift. So we start by looking at the Doppler effect. And the Doppler effect tells us that if a wave source is moving towards an observer, the waves get pushed together, so the wavelength gets shorter and the frequency gets higher. If the wave source is moving away from an observer, the wavelength gets longer and the frequency gets lower. If this happens with light, we call it redshift or blue shift. So blue shift happens if the wave source is moving towards you. So for example, a galaxy moving towards us, the wavelength gets shorter because the waves are compressed. The frequency gets higher. There are more waves per second. So we see the light has shifted towards the blue end of the spectrum. Okay, for redshift, the opposite is happening. So because the source is moving away from us, the wavelength appears to be longer, the frequency appears to be lower, and that's what we see with the vast majority of galaxies. Okay, there are a couple of galaxies that are moving towards us and have blue shift, but the vast majority of galaxies have a redshift. And what's interesting about the redshift, the size of the redshift, how much the frequency has changed, tells us how fast the galaxy is moving away from us. And what we find is the further away a galaxy is from us, the faster it's moving in the opposite direction. And what that tells us is that the space between the galaxies must be getting bigger. Now, if there's more space between the galaxies, it's going to move at a faster rate. And that tells us that the universe was once really small and provides evidence for the Big Bang Theory. So, what is this Big Bang Theory? Big Bang Theory is the theory that tells us that the universe used to be really, really tiny, and then there was a massive explosion and it started expanding very rapidly. Now, it's a theory because we can never prove it. We can't go back in time to see the Big Bang happening, but all our evidence points towards it. So the two key pieces of evidence you need to know about. The first one is redshift that we've already discussed, which tells us that the universe is the galaxies are moving apart. And the second one is the CMBR, which stands for cosmic microwave background radiation. And that's just the energy left over from the Big Bang. The redshift can be used to describe several different theories of the origins of the universe. CMBR is only supports the Big Bang Theory. So the fact that that exists tells us that the Big Bang Theory is the best theory we have for how the universe began. The last thing I want to go through in this video is some key terms about how science works. So we'll start with precision. The precision of a measuring instrument tells us the smallest thing that can measure. So for example, if I have a ruler, usually the precision of that is going to be 1 millimeter. I can measure to the nearest 1 millimeter. If I have a measuring cylinder, I might measure to a milliliter, or I might measure to 5 milliliters. So it's what the smallest division is. The interval in my results is the distance or the difference between the two nearest results. So if I measure 5 centimeters, 10 centimeters, 20, then 5 centimeters, 10 centimeters, 15, 20, then the interval would be 5 centimeters. The range is the difference between the maximum and the minimum. So 20 to 5 or 5 to 20. Okay, a variable is continuous if it can take any value. Sometimes they will ask you that one. And then you need to be able to identify independent, dependent and control variables. So an independent variable is what has been deliberately changed in that experiment. A dependent variable is the thing that is changing as a result, the effect that you are trying to measure. So if I was seeing how distance affected force, the dependent variable would be the force. That's what I'm measuring, that's what I'm finding out about. And then control variables are things that are being deliberately kept the same in order to stop them having an impact on the result. So for example, in an experiment, we might want to keep the temperature the same, because otherwise that will affect the speed that something happens at, for example. Okay, whatever you do, don't say fair test. It's so that the results aren't affected. Okay, so graphs, you need to know that we draw bar graphs if the independent variable is a categoric variable. So for example, eye colour. Line graphs are when the independent variable is continuous, so that means it can take any value, as we just discussed. So something like height would be a continuous variable. Then for describe the graph questions, you want to try and give as much detail as possible. If it's only 1 mark, just say what the general pattern is. But if it's more than 1 mark, you might want to talk about how the pattern changes. Mention maximum or minimum points. Mention wherever there's a change in the steepness of the graph. Try and figure out what the steepness of the graph represents and talk about that as well. Then the last thing I want to talk about is how we do research. So the first thing you need to look at is how we avoid bias. So if we have a mobile phone company, they like asking about those, who wants to do research into the safety of mobile phones. If they pay a company to do that research, then there could be bias involved. The company might be being paid for finding positive results. So researchers always say who has paid for it, and preferably an independent company should be used, so one that isn't the company that produces the mobile phones. To change scientific ideas, we need to find new evidence. Often new evidence is found when we have improvements in technology, for example. And if that new evidence doesn't support the existing theory, then what we have to do is we have to try and gather some more evidence. So we get our first piece of new evidence that says the theory doesn't work. We don't know if that evidence is correct at first because there may be errors in the results. So we repeat it, we find more evidence. Either that will say, well, our first evidence was wrong, or it will say that our original theory was wrong. If our original theory was wrong, then scientists will have to suggest a new theory that does support the evidence that they have. Okay, thank you for watching and good luck in your P1 exam.